In our previous video, we had just been looking at this reaction of the silver sulfide decomposing to make silver metal and S8. And we did a calculation where we calculated how many grams of silver we could collect. So just to review, we started with 235 grams of silver, and we did the calculation here where we figured out what the molecular weight of the silver was. That's this number right here, 247.80 grams per mole. And when we did this calculation, we wanted to know how many grams of silver we did. So just to recap our process, we're working with this flow-through process where we start with grams of A, or sometimes with moles of A. And A is the starting material that we always have to decide what it is. In this case, it was silver sulfide. And then we go to converting that to moles of B. And sometimes we ask for all the way to grams of B. And B is the other material that we're interested in, which in this case was silver. So in this process, we're using the molecular weight of A to convert grams to moles. That's this step right here. Then we use the balanced equation to convert moles of the silver sulfide to the moles of the silver. That's this step right here. And then if we are asked to, then we use the molecular weight of B to calculate how many grams of our second material, and that was this step right here. So what we just calculated here is called the theoretical yield. The theoretical yield is the maximum amount of stuff we could calculate if we use up all of our materials. Now, if we were actually running this experiment in the lab, the reality is that we probably wouldn't get a 100% efficient reaction, and so we would have some other yield, which we call the actual yield. So let's imagine a scenario where we run this reaction, and instead we get 189 grams of silver that we collect. This is the actual yield. Most often in the laboratory, what we do is we talk about the percent yield. And the percent yield is just whatever the actual yield is over the theoretical yield multiplied by 100%. So if we did this calculation, we would get 92.2% yield. So that would be a pretty good yield. So what you'll see in lab is that most often your actual yield is less than your theoretical yield. Every now and then people will find that their actual yield is higher than their theoretical yield, which usually means it's either still wet or there's some kind of an impurity in here and we didn't fully separate it. Sometimes it's just starting material that we didn't get to use up. But let's go ahead and try another practice problem. So let's try the reaction of silver nitrate with calcium bromide to make silver bromide and calcium nitrate. Now, before we go any further, I want you to stop and look at this reaction and tell me, is this a balanced reaction? It's really not, right? So take a second and balance it. Pause the video so you can do that. This was a fairly simple one to balance. We end up only needing 2 silver nitrates and 2 silver bromides in order to balance it. Now, one of the things I want you to start paying attention to are the phases of matter. And I'm going to start putting them in the reactions that we're looking at so that we can start learning additional pieces just while we're doing other things like talking about gram to mole conversions and stuff. So this reaction here, notice that we have aqueous, aqueous, solid, aqueous. So we put 2 reactions together that look like probably water. They're usually clear, colorless solutions. Every now and then they have a color, but we would have silver nitrate and potassium bromide. We'd add them together and they'd make probably a cloudy solution, but eventually the silver bromide would settle out. So that would be our solid. And then the rest of the calcium nitrate would be dissolved in the water. And that's what aqueous means. It means dissolved in water. So this is a precipitation reaction. And the precipitation reaction is any reaction where we start with things that are dissolved in water and we end up with at least one solid material here. Most precipitation reactions are going to be ionic compounds. And notice what else was happening in this reaction. Notice that over here in our first material, we had silver nitrate, which we know is a silver ion and a nitrate ion. And we have two of those, so I'm going to draw them twice just to kind of visualize this. And then we had a calcium bromide, which is also dissolved. And so calcium we know is calcium 2+, and bromide is bromide minus, and there's two of them, so I'll draw them both. And then this silver bromide we know is silver with bromide, and there's two of them. And then we have calcium and nitrate. And there's two of the nitrates. So we can visualize the balanced equations, but look what happened. When we did this reaction, the nitrates were hanging out with the silvers before, and now they're hanging out with the calciums. They swapped which cation they're hanging out with. And the same thing is true for the bromides. The bromide started with the calcium, and then it went, and that bromide hung out with the silver and formed a solid precipitate. And so this little unit of silver bromide, these guys are all stuck together and not floating around anymore in the solution. So when we have this precipitation reaction, although this may not happen every single time, this kind of a pattern in our reactions where we just swap the cation and the anion pairs is very common. So keep your eye out for it. It also means that it's very simple to balance because we can keep those ions together. We don't have to separate out the nitrate. We can just, kind of stick them as a unit. All right, so this solid thing over here is called the precipitate. And then the rest of the thing would be called the solution. And here's the precipitate. And so they say in chemistry, if you're not part of the solution, you're part of the precipitate. And yeah, that's supposed to be a joke. But no problem. We're going to come back to this balanced equation. I'm going to rewrite it so it's easier for us to take a look at while we do our calculations. So we said it was 2 silver nitrate that are aqueous and 1 calcium bromide. And we're making 2 silver bromide, no longer dissolved, and calcium nitrate. And that's also soluble. Okay, so let's do another calculation. Let's imagine that we have 1.84 moles of silver nitrate, and we want to know how many grams of silver bromide would we expect to collect. So this is a question of what would be the theoretical yield. So let's review our strategy. Our flowchart says grams of A to moles. I should make this lowercase because that's what it is. Moles of A, moles of B, and grams of B. So your first step is to identify A and B. And then I want you to identify where are we starting on this flow chart and where do we end. So where on this 4-step process are we getting on to this flow, and then where are we ending on this flow, because it can vary and that's going to affect what steps we use. And then I want you to set up the units. So give this a try. Pause the video and try it, and then turn it back on and we'll do it together. Okay, so coming back together here, we start with 1.84 moles of silver nitrate. That's the thing that we know how much it is. So this is our A. And then the grams of AgBr. AgBr then is our B. And this also tells us where we're getting on. Because we're starting with moles, we're actually starting in this second step along. So let's review that process. We're going to take the balanced equation and we're going to convert from moles of A, silver nitrate, to moles of B, silver bromide. And then we're going to use the molecular weight of B to convert from moles of B to grams of B. So when you set up those units, I hope what you did was you started with 1.84 moles of silver nitrate. And then what I mean by setting up the units is before you put in any of the numbers, you don't actually have to do that yet. You can just say, all right, I have 2 calculation steps. How do I know I have 2? Because I put 2 of these guys here in red. Each of these means 1 calculation. So I have 2 calculation steps that I'm going to do. So let me look at the units. I want to go in this first step from moles of silver nitrate to moles of silver bromide. So I'm going to put my units where they can cancel out. I want to cancel out the moles of silver nitrate, and I want to end up with moles of silver bromide. The units that I want to get rid of, I put in the bottom so that they can cancel out. And the units that I want, I'm going to put in the top. Now I can look at the units of the next step. Look, I haven't even put in any numbers yet, and that's fine. In the next step, I'm going from moles of B to grams of B. So B was silver bromide, so I want to divide out the silver bromide. So my moles are going in the denominator, and I want my grams to stay where they are. That's what I want to end with. So that needs to be in the numerator. And so I can see that those units would cancel out too. So now let's put in those numbers. Our balanced equation tells us what numbers go in this ratio. So let's go and look at how many moles of silver nitrate there are. Over here in the balanced equation, we can see there's 2 moles of silver nitrate. So we put a 2 in front of that moles of silver nitrate. And then we go back to the balanced equation and look for the 2 moles of silver bromide. And so we're going to put a 2 right here. They will cancel out, but that's okay. We're still writing them in as they are. Next, when we look at molecular weight, we know that we write molecular weight as grams per mole. So we'll have 1 mole here because it's always grams per 1 mole. Now, when we calculate that molecular weight of silver bromide, I got 187.77 grams. So when we review this setup, we can see all our units cancel out. We are ending up with the units that we want. This was the units that we wanted, grams of silver bromide. So now we can just run this calculation. 1.84 times 2 divided by 2 times 187.77. So if you do that, I got 345 grams of silver bromide. I'm using multiplication rules here, so I have to keep the smallest number of significant digits, which is 3 right here. So this number that we calculated, this would be our theoretical yield. Now, what if our actual yield was really 292 grams of silver bromide? Go ahead and calculate the percent yield. If you need to, scroll back and look at what the previous calculation was. All right, it should be 292 divided by 345, both grams, so the grams cancel out, multiplied by 100%, which in this case would give us 84.6%. So this concludes our short video on percent yield, and I'm going to continue in the next one, actually right where we left off, and we're going to talk about limiting reagents in that next problem.